Hi, let's continue with our Coulomb's law examples. So consider the point charges as shown below. We have in here the given charges, the Q1 situated at the center, charge 1 with the magnitude 1 times 10 to the negative 6 Coulomb, and charge 2 to the right, magnitude negative 2 times 10 to the negative 6 Coulomb. And we have charge 3, positive 3 times 10 to the negative 6 Coulomb. So let's label the sign of the charges. Q1 is positive, so let's label this as positive. And for our charge 2, we have negative, and charge 3 positive. Okay, and the distance between charge 1 and charge 2, this one, is equal to R12 with magnitude 10 centimeters or just equal to 0.1 meter. And for the distance between charge 1 and charge 3 is R13, which is equal to 15 centimeter. Okay. So our problem, compute the net force experienced by charge 1 due to the presence of Q2 or charge 2 and charge 3. Okay, we can solve this using vector addition. So we need to calculate the force on the charge due to the individual charges and add them using vector addition by component method. So this is the principle of superposition. So we need to label the direction of forces for us to have vector notations so that we can add this in vector component method. Take note that charge 1 would experience an attractive force due to the presence of this negative charge Q2. So attractive. So therefore, the force experienced by charge 1 due to charge 2 would be in this direction. Okay. This is our F12. And going to the right. How about the force experienced by charge 1 due to the presence of charge 3? Take note that the two are of the same sign. So, charge 1 would experience a repulsive force. So, this is in opposite direction to our charge 3. So, down. Okay. So, let's label this as our F13, or the force experienced by charge 1 due to the presence of charge 3. Our FBD would look like this. So this is our F12 and this is our F13. And the angle between this, since this is 50 degrees based on our original graph. So this is a given angle 50 degrees. Therefore, the angle here is equal to 40 degrees. So solving by component method, the F net would be equal to the component summation of all the components along x and y. F12 along x-axis, positive x-axis, plus we have F13, but then take note our F13 is 40 degrees below. So by component, the component of F3 along x-axis is just equal to F13 cosine 40 degrees. So this is our x component or the I hat, and then plus our y component. We only have one vector component. So F13, but downward, so negative. And this is sine 40 degrees, j hat. Again, this is our summation of forces along x-axis, and this is equivalent to our summation of forces along y-axis. But we need to determine what is F12 and F13 in magnitude so that we can plug in. So solving for F12 and F13, we need to apply or use the Coulomb's law. So by definition, Coulomb's law, the magnitude of F12 is equal to K, the interacting charges, 1 and 2, over the square of the distance between these charges. So this is plugging in the just plugging in the values. 9 times 10 to the 9 Newton meter squared per Coulomb squared for the K, and then the magnitude of our charge 1 multiplied to the magnitude of our charge 2. So these are all given values, and the distance between them 10 centimeters or 0.1 meter, and then square. So this is equal to 1.8 Newton in magnitude, because meter square cancelled here, and then the Coulomb square cancelled to the two columns, the Coulomb unit of our charges. So that's the magnitude for F12. And then how about F13? The F13 magnitude, applying again the Coulomb's law, this is equal to Q1 and Q3 over the square of the distance between the two charges. Plugging in the values, Newton meter squared, Coulomb squared, times 1 times 10 to the negative 6 Coulomb, times 3 times 10 to the negative 6 Coulomb, over what's the distance between them. This is equal to 0.15, and the value is just equal to 1.2 Newton. So the net force, plugging in this to our component method equation. So you know that F net, or the value for summation of forces along x, is just equal to 1.8 Newton plus 1.2 Newton cosine 40, and this is equal to 2.72 Newtons. And how about summation of force along y? So we have, and then sine 40, which is equal to negative 1.2 Newton sine 40. This is just negative 0.77 Newton. So knowing the I hat and j hat, or the components along x-axis and y-axis respectively, we can use these values to determine our net force. It's just equal to the square root of the sum of the squares of these components. This is our x component and the y component. So plugging in, so we have the square of 2.72 square plus the component along y, which is equal to negative 0.77 Newton square. So this is equal to 2.82 newtons. So this is now our answer, the magnitude of our net force. And the tangent theta for this, to determine the direction, which is equal to the opposite, 0.77, the y component, over the adjacent, the 2.72, which is the x component. And this would give us a theta equal to negative 15 degrees. And this is now the graph of our resultant vector. This red line represents our net force, or the net force experienced by Q1 due to the presence of Q2 and Q3. What if we are asked to find the force experienced by Q2? So instead of Q1, this time our focus is the charge Q2. Based on the diagram, the force between Q2 and Q3 is attractive. So writing the FBD in here, the F23 or force on charge 2 due to the presence of charge 3 would be in this direction. And we don't know yet the angle between the horizontal axis and the F23. And checking also the force of attraction between Q2 and Q1. Of course, since they are of different signs, then this is also attractive. Therefore, in our FBD, since this is the position of our charge 2, the attractive force is towards the left. So this is the force on charge 2 due to 1. So our FBD of the forces acting on charge Q2 looks like this. So we need to determine the distance between charge 3 and charge 2, since we already have the distance of our charge 1 and charge 2, or between these two charges. But we do not have the R23, or the distance between Q3 or charge 3 and charge 2. So applying the sine law, since we have a triangle that looks like this. So this is the position of our Q1, then the Q2, and the Q3. The R13 given is equal to 0.15, and R12 is equal to 0.1 meters. But R23 is yet to be computed. So if we label this angle as our angle A, so this side is our A, side A, and if this angle is B, this side is our side B, and if this is our C angle, then this is equal to our side C. Applying the cosine and sine law, so our review, cosine law is equal to C squared, A squared plus B squared minus 2AB cosine C. So in our example, A is equal to 0.1 meter, B is 0.15 meter. We do not have angle B, and our C given is 140 degrees. And how about our side C? Still unknown. So let's compute. Solving for C squared, just plug in the values. It's 0.1 square plus 0.15 square minus 2 times 0.1 times 0.15 cosine 140. So this is equal to, C is just equal to 0.24 meters. So this is our equivalent R23, or the distance between charge 2 and charge 3. And how about angle B? We need to determine angle B. In this case, let's apply the sine law. From the equation sine law, so B over sine B is just equal to C over sine C. Thus, substituting the values, we have 0.15 over sine B equals 0.24 over sine 140. Sine B, therefore, is just 0.15 sine 140 degrees over 0.24. Thus, RB is just equal to 23.7 degrees. We need this to solve our net force. So this is now, based on our graph, this angle B is just the angle theta in here. So having the r, or distances between charges, and the angle, we can now solve the net force on charge Q2. Since we already have our values for F21, why? F21 is just equal to, in magnitude, F12. So meaning this is just equal to 1.8 newtons. So only in magnitude, but they differ in direction. So what we need to solve is the force on Q2 due to the charge 3. So this is equal to, using the Coulomb's law, so this is equal to K Q2 and Q3 over the distance between these two charges, 2, 3 square. Plugging in the values, we have 9 times 10 to the 9 Newton meter square over Coulomb square, and the values for the two charges, 2 times 10 to the negative 6 Coulomb and 3 times 10 to the negative 6 Coulomb, all over distance, square of the distance between them, 0.24. This is equal to the side C that we computed earlier. So the F23 therefore is equal to 0.94 newtons. Since we have now the values for the forces on Q3, therefore we can solve the net force on this charge using component method. So applying the component method, the if net is just equal to, what's the component along x? So we have negative F23 cosine 23.7 degrees, the angle between F23 force with respect to the horizontal, minus, still negative since that's in the left side of our xy axis, so negative F21. So you need to review your addition of vector using component method. This quantity is our x component, so I hat, plus the y component. We only have one vector, this one, the F23, the y component of this vector. So F23 sine 23.7 degrees. So this is our y component. So plugging in the values, we have negative 0.94 Newton cosine 23.7 degrees minus 1.8 Newton. So this is equal to the x component, I hat, plus we have 0.94 positive Newton sine 23.7 degrees j hat. So computing, we have the x component equal to negative 2.66 Newton I hat plus 0.38 Newton j hat. So the magnitude, therefore, since this is in vector form, so the magnitude on Q2 is just equal to the square root of the sum of squares of the component, the x and y components. So we have negative 2.66 Newton square plus 0.38 Newton square, and the square root of that, this is equal to 2.7 newtons. So this is our answer. This is the net force experienced by Q2 due to the presence of Q1 and Q3. But what is the direction? So computing for the angle, this is equal to tangent theta, y component, equal to 0.38, and then adjacent, that's the x component, equal to negative 2.66. So then, solving for theta, the inverse tangent is equal to just negative 8.13 degrees. So this is the angle. So if we are going back to our diagram, So going back to our FBD, the position and direction of our net force on Q2, if net, would be in this direction, in this quadrant. So with the angle theta in here, which is equal to 8.13 degrees. And negative, since it is in the second quadrant. What makes it negative? Because of this value, or the x component is negative. So just a review in this example, if you need to determine the force on Q1, write an FBD of forces with Q1, position Q1 as your point of origin. Again, Q1 and Q2, what is the FBD direction? The two forces are attractive. So therefore, the force 1, 2 should be towards Q2. So this is the direction of F1, 2. How about the direction of the force due to Q3 on charge 1, or the F1, 3? Since repulsive, so the direction should be away. So towards this direction. This is the F1, 3. So, and then you need to determine the magnitude of F1, 2 and F1, 3, and the distance between this R1, 2 and R1, 3 to solve for the magnitude of these forces using Coulomb's law. And then if you want to determine the net force on Q2, so again, checking the direction of forces, the F23 should be attractive. So the reason why F23 should be in this direction in your FBD. This is F23. How about 1 and 2? Since attractive, because they have different sign, so this is now the direction of our F21. And again, to know the magnitude of these two forces, you have to use Coulomb's law. So what you need, the magnitude of the charges and the distance between them. The reason why we computed for the R23. But the R12 is already given, so there's no problem. And then how about for Q3? If you're asked to determine net force on Q3 due to the presence of Q1 and Q2. So checking again the direction between charges 3 and 2, this is attractive. The direction should be, if this is your point of origin now, since your focus is charge 3, so the direction should be towards Q2 since this is attractive. So in this direction, this is F32, meaning the force experienced by charge 3 due to charge 2. And how about 3 and 1? So we know that these two charges have equal sign. So the force should be repulsive. The force to 1 should be away from charge 1 in this direction. Of course, along the line joining charge 3 and charge 1 is this direction. F3, 1. So you need to solve for the F32 and F31 using Coulomb's law, and then finding the net force. Again, apply the component method that you've learned in your previous physics course. Thank you.